Interference is a phenomenon that happens when two or more than two waves are meeting one with the other. For example, let's say that I have a pulse that is traveling to the right in my picture, and then I have another pulse, maybe with a smaller amplitude, that is traveling to the left. When the two waves meet together, they create a third wave that is exactly the sum of the two together. So let's have it a little bit more higher wave, because it should be the sum of the one on the left plus the sum of the one on the right. So if, for instance, the amplitude here is maybe 3 meters and the right wave has an amplitude of 1 meter, the new wave will have, or the new pulse in this case, because of the superposition principle, will have an amplitude of 4 meters. Now I would like to see some simulation. If I have here one drop of water that is falling on a pond, a wave is formed with the maxima and the minima. I can also see this represented on a graph, a maximum of the wave and a minimum of the wave. If I add a second drop into the pond, this second drop will create another wave that will interfere with the first. So you will see this strange representation that are called interference images, where you have a zone with no wave, with a minimum here, no wave at all, and a zone with a maximum. So a zone with a maximum of interference and one with a minimum of interference. Going back into my page, let's say that I have one wave that is traveling like this, and I want you to imagine a second wave that is traveling and meeting the first wave with the two maxima together with maxima. In this case, you will have a constructive interference. The result of the superposition principle will give you a wave that has the double of the amplitude. If instead you have one wave and the second wave, just allow me to draw it in front of it so we can see it better, that is at 180 degrees switched, and the maximum is instead meeting with a minimum. In this case, the two waves are cancelling each other. So you have what is called a destructive interference. Let's see this phenomenon in the simulation with the light. I have two sources of laser green light on the left side of the screen, and on the right side, just in front of them, I will place a screen, like a wall, and I'm sending the first laser light through this wall. The light is a wave, and here you can see the maxima and the minima of my wave. And now I'm adding the second source of wave. And like in the water, interference images are starting to form. You will see the light, the bright and the dark. They are called fringes, so the bright fringes and the dark fringes that are alternating. And now let's see what happened on the screen. Technically, if I'm thinking the light as just a particle, I will expect to see on the screen one green spot in front of the first laser and a second green spot in front of the second laser, and nothing much more, nothing else. At the beginning of 1800, Thomas Young discovered that when the sunlight was shining through a tube opening placed cut on a card box, let's say, so when the light of the sun was shining through two slits on a far distant screen, there were strange images forming, and those are the ones that we're seeing now on our screen. And maybe if I do like this, we can see it even more. I separate in this case my two lasers, and on the screen there are not only two dots, but there are plenty of other dots. Actually, they are called fringes of interference. I have the maxima, or the bright fringes, and I have the minima, or the dark fringes. So Thomas Young realized that the result on the screen that the light is producing when it's interfering with another source of light is the same as the water waves when they are interfering. If you just think maybe of two ducks that are walking together, swimming together on a pond, this is what you will see, interference images. So Thomas Young said that then the light behaves like a wave. And now the typical question is, okay, let's imagine to have a screen placed on the right side here, like I have the screen on my simulation, and then place this time two slits, and have some source of light that is coming toward the two slits. So the source of light I represent it here with my line that are the maxima, like you imagine here the wavelength going like this in this wave. And at each opening you have a new wavelet forming. In my picture I only represented the direction of the wave with an arrow, but you want to imagine the same representation that you have on the left of the screen. And I'm looking now at the point P that I called up there, and I'm saying, okay, if that is the path of one wave coming from the source number 1, and the second is the path from the second wave interfering with the first at the point P, what is P, a maximum or a minimum? So how can I find out a relation a mathematical relation that will tell me whether P is a maximum or a minimum? Now let's erase a little bit here so we have more room. Let's call the distance between the two slits just little d. And then I will call the big L the distance between the screen on the right and the slits on the left. My waves have different patterns. The wave coming from the slit number 1 looks like it's covering less distance than the wave coming from the slit number 2. This difference in distance, let's call it delta x. And if I call theta the angle formed in this right triangle, green, purple, and yellow, this angle theta helps me to find the delta x, because I would say d sine of theta is the change in path. Now, if this change in path, and let's look at here if I have one wave, if this change delta x is an integer multiple of the wavelength lambda, where m can be 0, 1, 2, etc. So imagine just it's equal to 1, and I'm looking at the starting point. So if the second wave starts a lambda farther away, let's say like this, the two waves are meeting together with maximum and maximum, so I will have a constructive interference. If instead, and let me draw again the first wave, the path difference, in my previous picture, this is the path difference. It's like I have the source 1 and the source 2 that are starting slightly at different distances. So if instead the path difference is equal to half lambda, and let's say that I'm counting here, so this will be lambda, and half lambda is at the center over here. So if I place my second wave starting right there, the two waves, actually not like I did, sorry, the two waves are just in opposite phase. So they are giving me a destructive interference. And this happens when I have a multiple of half lambda. A way to write it is to say m plus 1 over 2 times lambda, where m is again equals to 0, 1, 2, etc. Just an integer number. Now let's go together and place back the delta x as a d sine theta in this part. So I have here that when d sine theta is equal to m lambda, I have a constructive interference. If instead d sine theta is equal to m plus 1 over 2 lambda, I have a destructive interference. In the picture on the right, I have reported, it is represented, the amplitude of the wave, better, the intensity of the wave. And also you can see that are reported the different values of m and what they are giving to me. Let's look at the lower side of this picture and see, for example, m equals to 3. That m equals to 3 corresponds to a minimum in this case. So this corresponds to a minimum, or also you can say that corresponds to the third dark fringe. And you will obtain that placing in the equation of the destructive interference m equals to 3. Let's now look at another number. For example, let's look at the part in the picture that is marked above, and let's look at the number 2. 2 corresponds to a maximum. So this will be called a maximum of interference, or a bright fringe. Precisely the second bright fringe. And you will obtain this placing instead of m the number 2. Notice that the 0 is the central bright spot. So when you substitute m equals to 0, you will have the central maximum. Or if you, in the destructive equation, you substitute the 0, the two zeros, you have the minima. Sometimes you represent the interference pattern in this way. Let's say that I have the two slits. This is my section of the two slits. And then a little bit farther on the right, I have the screen. Let's say this is my screen. I will have a central bright spot, and then the next bright spot, and the next, and again the next, and this one is my central bright spot, and symmetrically down below, exactly symmetrically, I have another bright spot, and so on. This first is called the central maximum. Is a constructive interference with m equals to 0. Then you have the first maximum that is with m equals to 1, and of course you have symmetrically down below the same thing on the up and down the central maximum. Then you have the second maximum, so the second bright fringe, the second constructive interference with m equals to 2, etc. And where did I not use the color red? Let's say that my laser was red, so on this spot I have the first minimum that you obtain with m equals to 0 over there. Then over here you will have the second minimum with m equals to 1, and over here you have the third minimum with m equals to 2, and so on. Sometimes the part of the equation that is written as d sine theta takes another format. When you imagine that the screen is very far away with respect to, is very large in number with respect to the distance between the two slits. In this case, you want to build the line that is hitting the central maximum. Let's say this is my, if the laser is red, with the central red maximum, and maybe at the point P also have a maximum of constructing interference. Then I connect also the central line with my point P, and I have an angle theta between these two lines. This angle theta is the same theta that was formed in my previous triangle at the connected with the two slits. And I can say that this theta becomes small. So in the approximation for the distance screen, in the assumption that the screen is far away, instead of sine theta, I can approximate the sine theta to simply theta, and better, theta can be approximated to the tangent of theta. If you try with small angle, the sine of theta small in the calculator gives you the same value as the tangent of theta. So you can say that the tangent of theta is equal to, and if I call y the distance between the central maximum and the point P, pretending that the screen is my y-axis, I have that the tangent of theta is the ratio of y divided by L, where L is the distance over here between the screen and the slits. Now I can rewrite my constructive and destructive formula in an alternative way when you are working with a faraway screen that says that d times y divided by L equals m lambda, or d divided by y times y divided by L equals to m plus 1 over 2 lambda. And essentially these two formulae over here are the one important for the interference pattern. Let me make them in a box, where m again is an integer number that can be 0, 1, 2, etc.